afternoon, and thank you for attending. Today's webinar is Musings of an Apps Chemist, presented by Roger Bardsley, who is our Applications Chemist. We will be taking questions at the end of the presentation, so feel free to submit them throughout using the question function. Okay, Roger, I'm going to turn it over to you.
Thank you, Shelley. Again, welcome everybody. Good morning, good afternoon, depending on what time zone you're in. Hope everybody out there is having a good day. Give me just a second here. What I'd like to talk about today is when we introduced the Lumin, we looked at a lot of different parameters that you could change. The purge time, the purge flow, the dry purge time, the dry desorb time, and created an app note or a technical note talking about these different parameters that you could change on the Lumin itself for purge and trap. It's available on our website, teledynetekmar.com, and if you go there, just follow the tabs to see that. But we got to thinking, what about the GC init parameters? What methods, what parameters could we change to possibly improve things? What effect does it have on all these different applications? We're going to talk a little bit about the cookbook methods. As we look at the GC parameters, what effect does constant pressure have? What does the liner, size of the liner, have to do with how the data is presented? First of all, for those that aren't overly familiar with the GC, I'd like to talk a little bit about GC, which was originally called back in the 50s gas-liquid chromatography. What happens is you have a gas phase that interacts with a liquid phase that's absorbed onto the column or coating the column. And by changing that liquid phase, you can change the interaction of different compounds. One of the best examples of this that I could find is the blood alcohol conformation column. As we can see here in this slide, the methanol peak actually moves past the acid-aldehyde peak, and the acid-aldehyde peak moves in. The same switch occurs with isopropanol and acetone. Again, just showing that the liquid phase can have some aid in your chromatography. Going on to the cookbook methods, typically what we do here are 8260 and 524. From 8260, it says the effluent from the trap is sent to an injector, operating a split mode for injection to a narrow bore capillary column. The column is temperature programmed to separate the analytes, which are then detected on a mass spectrometer interface to a GC. And that's out of the 8260 method. In there also they talk about different chromatography columns. And I'd like to say that, and I highlighted in blue, however, they are not based on preferential order. It's just their ability to achieve the project-specific data quality objectives. And here they list 5 of them. You can use whatever column you would like. So there's really no recommendation in this type of cookbook method. The one that we focus on and we use here is column number 5, the 20 meter 0.18 ID column. In terms of purge and trap, the recommended chromatography conditions are examples based on assortments of an analysis used. The actual conditions will be based on what you're currently using. Again, gives you a little bit of guidance, but not a lot. When you go to the split injection for column number 5, it suggests a 0.9 mils per minute with an initial temperature of 30 degrees. We start at a different temperature. We start at 35 because for the GC systems to cool down to 30 takes a lot longer. So that's why we kind of focus on 35. And again, the split ratio is based on the GC itself. The 2 program temperatures that we used for this work on 3 different GC systems that we have here in the lab. 2 of them we used 35 degrees for 2 minutes, then 10 degrees C to 100 degrees, and then we bumped it up 25 degrees per minute to 225 for a final hold of 2 minutes, for a total runtime of about 15.5 minutes. The other parameter we used was 35 degrees for 2 minutes, then we did a slight ramp of 5 degrees per minute to 45, then we ramped it up again 14 degrees per minute to 100, and then again 25 up to 225, and we were able to, with a final hold of 2 minutes, we were able to get that retention time down to about 14.93 minutes. What I'm going to talk about for these first couple ideas are the standard curve response factor percent RSD. The response factor is calculated by taking the area of the compound times the concentration of the internal standard, and then dividing that by the area of the internal standard times the concentration of the compound. So what you get is a response factor for each standard data point. So at 0.5 ppbs for chloroform, the response factor was 0.512. At 1, it was 0.503, etc., etc. Then we take the relative standard deviation of that, and that's where what we're talking about when we talk about the standard curve percent RSD. Just kind of wanted to clarify that because some people may not totally understand that part when we're talking on this webinar. So, what about the pressure? What I'd like to do right now is start a poll and see what you're currently using in your lab, either constant flow or constant pressure. So if you could vote on that. We'll give you a few minutes to vote on that, please. And when the poll is closed, we'll provide you those results. Okay. I should be sharing the results now. Looks like 72% are doing constant flow, 28% are doing constant pressure. So for the pressure experiment, what we did was we took an 82-60 mix. We included the acetates, California oxygenate, gases, cleave, ketones, about 99 compounds. We created a calibration curve from 0.5 parts per billion up to 200 ppb. For the flow part of the experiment, all 3 GCs were operated at 0.8 mils per minute. We also then turned them around and did the same thing with the pressure. On one GC it was 115 kilopascals, another GC it was 16.4 psi, and the third was 16.115 psi to meet this 0.8 mil per minute at the start. Again, that's at 35 degrees. The columns we used was a 20 meter 0.18 1 micron film thickness VMS, and another one we used was a 20 meter 0.18 millimeter ID 1 micron film 624 column. The liners for this one was all a 1 millimeter ID split liner. And as you know, with constant flow, the pressure will increase, but the linear velocity stays the same. When you do it by constant pressure, the flow does decrease. And watching the GC, we've noticed the flow decrease from about 0.8 mils per minute down to when it reaches the final temperature of about 0.36 mils per minute. The linear velocity, because of that flow changes, also decreases. So it went from about 39.7 centimeters per second down to about 28.6 centimeters per second. The one thing we did notice too is, and hadn't thought about this, was the mass spec pressure actually drops during the run due to that lower flow going into the mass spec. So let's look at the flow to pressure comparison for GC1. As you can see out here in the naphthalene regions, the 3 compounds elute a little bit later on the constant pressure versus the constant flow. So we're going to look at those 3 compounds out there. Specifically, I'm going to look at the mass 180 for the 1,2,4 trichlorobenzene and the 1,2,3 trichlorobenzene. So looking at those, as you can see, with constant flow, they come out about 12 minutes. With constant pressure, they move out closer to 13 minutes. Looking at this mass, the other thing I want to point out is, as you can see, the peak width does broaden as the compound goes through the column a little bit longer. So you get a little bit of peak broadening with the constant pressure. We really didn't see a lot of differences in resolution for some of these compounds back in the base area. So back in through here, really didn't see better separation. I think part of that is because the peak width increased. Going on to GC number 2, same parameters. We did use the different temperature profile on this one, and we can see hexachlorobutadiene starting to separate out from the trichlorobenzene. But again, we still see that lengthening of these compounds at the final end of the run. Again, looking at those on GC2, the peaks also broadened with the constant pressure versus the constant flow. Moving on to GC number 3, same thing, constant pressure. This used the 624 column, and as you can see, the hexachlorobutadiene is separated out here, but we still saw the same effect with the constant pressure. These later compounds come out a little bit later on the column. And again, looking at the masses for 180 for those 2 trichlorobenzenes, we do see a broadening of the peaks like we saw in the other 2 GCs. So, in conclusion, constant flow or constant pressure, we didn't see any massive difference in the standard curve percent RSDs for these. The only thing that could be possible is on a constant flow. It could allow a shorter GC cycle time versus the constant pressure. So, what about the liner? What liner size does your lab use? So I'll let you vote for these 3. Let us know what size liner you may be using. We typically recommend the 1 millimeter for purge and trap. So I have a few more votes coming in. Everybody have your votes in? And as you see, about 65% of the attendees are using a 1 millimeter, 21% using a 2 millimeter, and 15% using the 4 millimeter. Thank you for participating in this poll. So for the liner experiment, we did the same thing. We took the 8260 mix, created a standard curve from half a ppb to 200 ppbs, held them both. We tested all 3 liners at both a flow rate of 0.8 mil per minute, and we checked it under pressure also. So we did 6 different experiments. We used the same 2 columns, but again, we varied the liners between a 1, 2, and a 4 millimeter. What do these liners look like for GC1 and 3 on the left? Those are the type of liners. The only 2 millimeter liner we could find for these GCs was one that had a little bit of a restriction in here and had some glass wool packing. For the other GC, again, the liners came in a straight liner, and we used those. Again, comparing the liners, we overlaid all the chromatograms for a 2 ppb standard, and everything looked like they overlaid fairly well for GC1. Blowing up that front region, again, you can see the difference between the 1 millimeter liner in the green versus the red versus the black for the 4 millimeter liner. And we really didn't see a drastic difference in any of the peak sizes or the peak shapes for the different liners for GC1. Moving on to GC number 2, the same thing. We saw a little bit of retention time shift, not sure why, if it was related to the liner or something else. But again, looking at the front compounds, again, all these compounds pretty much laid right on top of each other without a lot of differences between them. GC number 3, the same thing. I want to point out here, I have some issue with something that contaminated my water source, so I'm seeing this peak out here decrease a little bit over time. But again, looking at the front end of those compounds, again, not a drastic difference between the peak sizes or shapes or anything that really stood out that would have changed our relative standard deviation for the calibration curve. So in the liner size conclusion, it appears that size doesn't matter for purge and trap. It might make a difference if you're performing a direct injection where you need that volume for your direct injection to expand. So the people that were maybe using a 4 millimeter may be doing a direct injection on the same GC. So kind of wrapping up, this was a long study that created a lot of data and took a lot of time to generate and look at and analyze. And I got thinking, you know, tonight I'd like to go home and take it easy, maybe watch a movie. I got to thinking about spy movies and thought about Ian Fleming's Bond movies. But wait, what about the sample itself? Should it be shaken or stirred? So what we did for this one was we did the same thing, took the 8260 mix, half ppb to 200 ppb calibration curve we didn't use. We set the flow at 0.8 mils per minute, and we used a 2 ppb standard. So what we did on this experiment was we used a 500 mil volumetric flask. One of them, we stirred it gently and swirled it by just inverting it without creating a lot of agitation. The other one, vigorously shook it like I would have done in the pharmaceutical days, given a good vigorous shaking. We immediately transferred those samples to VOA vials, and then when we put them on the auto sampler, we alternated them, so we went stirred versus then a shaken, then a stirred, then a shaken. So if there was any variability in the GC during the run, we would see it across all samples. Looking at some of the data, as you can see here, difluoromethane and the 1,1,2,2-trichlorotrifluoroethane did show a significant difference between the shaken and the stirred. But most of the other compounds weren't that far off. Looking further down at some more of the compounds, the same thing. They're very close. So we only saw the two compounds that were drastically different. Here I also included the concentration that was calculated for the 10 samples, and then I did a percent RSD of the 10 samples. What was that concentration for those 10 samples relative standard deviation? I do want to show here on the surrogate dibromofluoromethane. Those, by the two different methods, were a difference of 0.9. So it really didn't matter that much on those. And I'd like to go ahead and put in here our final poll. How do you mix your samples? Do you vigorously shake them, or do you gently stir and swirl? So if we could go ahead and take a poll on those. Still getting some votes in. Looks like everybody's answered our poll. So go ahead and share those results. Again, 24% vigorously shake them, and 76% said they gently stirred or swirled them. Thank you for participating in the poll. I'll move on down some more of this data. And again, except for the two compounds, as you can see, there really wasn't a very big difference between being shaken or stirred. Keep thinking of steak and shake. Sorry about that. Again, toluene surrogate, fairly close, so you can see how close some of these compounds are. And this is all 99 compounds that were in our list. Again, bromofluorobenzene, just to show you how close the RSDs were on those, so you can compare them to some of the other samples. And the last three. So the mixing conclusion, stirring and swirling gently for two compounds appears to be better. However, if people are vigorously shaking them out there and not having difficulties, then continue to do that. For myself, I think I will not start vigorously shaking these samples, because we always look for those first 6 gases on the chromatography side. So in closing, I'd like to thank everybody for attending. I'll start taking questions here shortly. I just want to let you know some of the features of the Lumin Purge and Trap concentrator that we released last year.